Let's talk about the iterative hierarchy of pure sets. I'm Eric Steinhardt, professor of philosophy at William Patterson University, and you can learn more about me at my website, www.ericsteinhardt.com. So we're going to start with the iterative hierarchy. We're going to talk about sets and power sets. We'll then move on to talking about power sets in terms of selections and rejections. We will talk about selections and rejections as binary strings. We'll talk about power sets as sets of those binary strings. And we'll talk about the tree of strings. Then we'll talk about how to go from strings to pure sets. So, every set is surpassed by its power set. What's a power set? The power set of some old set is the set which contains all the ways of selecting or rejecting members of the old set. Let's talk about selections. We start out with a cute little puppy and a cute little tiger kitten. We're going to make some selections from them. And first of all, we don't want the puppy and we don't want the tiger. And that gives us a selection of neither. A selection that we'll express by the binary digits 0 and 0. Right? 0 means rejection. So we rejected the puppy, we rejected the tiger, that's 0, 0. And now we reject the puppy, we select the tiger, and we get a selection of 0 for the puppy and 1 for the tiger. So now we select, reject, and we get 1, 0. That's selecting the puppy, rejecting the tiger. Now we're going to select them both, and we get 1, 1 for selecting them both. So we have a set composed of the puppy and the tiger, right? And that set, those objects would be in brackets contained in the set. And the power set is going to be all the selections on the right-hand side, right? So there are 2 objects in the set, and there will be 4 binary strings in the power set. Generally speaking, the power set of a set with 2 members, right? The power set of the set puppy and kitten is a set of 4 binary strings. The power set of any set x, y, whatever x and y are, is going to be the set of those 4 strings. So the power set of any set with 2 members is the set of all bit strings of length 2. The power set of any set with 2 members is the set of all bit strings of length 2, and there were 4 of those bit strings of length 2. Let's go on and talk about selecting just one thing. We've got this beautiful parrot, and we're going to make some selections. We can reject it. We don't want that parrot, and that's a 0. We can select it. We like the parrot, and that's a 1. So, if the set is just a set containing the parrot, all the ways of selecting and rejecting give us the power set. The set with one thing makes a power set with 2 things. The power set of the parrot is the set 0 and 1. The power set of any set x is the set that contains 0 and 1. So the power set of any set with 1 member is the set of all bit strings of length 1. Again, the power set with just 1 member, the set of all strings of length 1. So, what about the empty set? What about it? It has 0 members. The power set of any set with 0 members is the set of all bit strings of length 0. Are there any strings of length 0? There's one string of length 0. It's the null string, represented by that upside down V. It has length 0. Selections. We've got nothing. Emptiness. Well, we can select, and all we can do with emptiness is reject it. You can't select nothing because there isn't anything there to select. So the rejection of emptiness gives us a null string, a string of length 0. Right? A set with 0 members gives us a string of length 0 in its power set. Given any original set, its power set is the set of all binary strings of length n, where n is the number of members in that original set. So, let's go over it again. The power set of the empty set is just going to be a set containing the null string. Power set of the empty set, set containing the null string. Power set of the set containing the null string is a set containing 0 and 1. So the power set of the set containing the null string is the set containing 0 and 1. Power set of 0 and 1 is going to be that set containing all binary strings of length 2. And there it is. The power set of the set 0, 1 is the set containing 4 binary strings of length 2. And now we come to the set containing those 4 binary strings of length 2. So that power set is going to include all strings of length 4. There are 4 strings in the original set, so the power set will contain every string of length 4. There are 16 of those strings. Only 2 of them are shown here. First, with all rejections, gives us 0, 0, 0, 0. Then all selections gives us 1, 1, 1, 1. So there we have it. Now the power set of the 4 strings 0, 0 through 1, 1 is going to be that set with 16 members. The power sets form a series of levels. The nth level in the series will be called V with n in parentheses, right? So this is standard set theoretic notation. The 0th level of sets, V0, is just the empty set. The next level, Vn plus 1, is the power set of the previous level, Vn. So let's work through a few of these. V0 is the empty set. The next level is the set of all strings of length 0. That means V1 is the set containing, should be an upside down V. The next level, V2, is the set of all strings of length 1. V2 is the set containing 0 and 1. There are just 2 strings of length 1, 0 and 1. The next level, V3, is the set of all strings of length 2. That's the V3. It's the set 0, 0, 0, 1, 1, 0, 1, 1. It's got 4 elements. The next level, V4, is the set of all strings of length 4. V4 is those 16 strings varying from 0, 0, 0, 0 to 1, 1, 1, 1. We can keep going from V4, right? There are 16 strings in V4, so V5 is the set of all binary strings of length 16, right? The power set is the set of all binary strings of length k, where k is the number of members in the previous set. So there are 65,536 strings of length 16. This means V5 has 65,536 members. The iterative hierarchy just now explodes. The strings in the iterative hierarchy can be arranged into a tree. The branches correspond to selections and rejections. Here's a simple way to put it. We started out with the set containing the empty string. If we reject it on the left side there, we get the string 0 in its power set. If we select it, we get the string 1 in its power set. Look what happens if we start with 0 and 1, right? Dashed lines correspond to rejections. If we reject both 0 and 1, we get the string 0, 0. If we select 0 and reject 1, we get the string 0, 1. Reject 0, select 1, we get 1, 0. Select them both, we get 1, 1. So I didn't draw the arrows, that would make it too cluttered, but that's going from one level to the next in a tree kind of form. Here it is, the glorious tree, right? The glorious tree of binary strings up to only, start at the first level, second, third, fourth, only up to the 4th level, V4, because I can't draw 65,536 strings on the screen. But there it is, a kind of platonic tree hovering in the abstract sky. Let's go from strings to sets. We had binary strings. Let's now convert. So we start with nothing up there in the upper left-hand corner. We reject it, and we get the empty set. Right? If you reject nothing, you just have a set that contains nothing, and so that shows us that the empty string and the empty set are equivalent. And we can think of it in terms of sets and power sets. The set that contains nothing, the empty set, makes a power set that contains the empty set. The power set of the empty set is a set containing the empty set. Let's keep going. We've got the empty set now, which is equivalent to the empty string, the null string. If we reject it, we get the empty set again. If we select it, we get the set containing the empty set. So you see some repetition here. So the string 0, is also equivalent to the empty set. So the empty set is equivalent both to the null string and the string 0, And the set containing the empty set is equivalent to the bit string 1. We've got our set, and we've got its power set. So the power set of the empty set is a set containing the empty set and the set of the empty set. It gets a bit dull repeating all these things. Here we go. We've now got the set and the set of the empty set as our things to select from. We can make 4 selections. There they are in the table, and we get 4 more sets. So if our set is up there in the upper red circle, the power set is there on the right, and you can see that the power set, and I'm not even going to read it. Too many brackets. It's a blizzard of braces. That's one reason that it's easier to introduce sets and power sets with binary strings. Well, here you go. Here's a bit of the iterative hierarchy. V0 is the empty set, V1 is the power set of V0, the set of the empty set, V2 the power set of V1, a set containing the empty set and the set of the empty set. And then we've got V3, the power set of V2, V4, the power set of V3, V5, the power set of V4, V6, V7, and so it goes. And if we display that tree of sets, just the first 3 levels, in terms just of pure sets. Those are sets containing only sets, the self-elaboration of the empty set. We have this tree. Of course, I didn't show you the next levels because I can't draw all those braces on the screen. But what a beautiful structure this is, floating in the abstract Pythagorean sky. So far we've talked about the finite levels of set, Vn for n finite. These ideas are easily extended to the transfinite. You can talk about Vl for L being any transfinite number, but that's going to be a topic for another time. Here we go. We've got the 2 rules for the finite levels of the iterative hierarchy of sets. V0 is the empty set, and Vn plus 1 is the power set of Vn. Thank you very much. This has been Eric Steinhardt talking about the iterative hierarchy of pure sets. You can learn more about me at my website, www.ericsteinhardt.com.